there, students. Welcome to lesson 16.2, solving exponential equations. So we're going to continue our work with solving exponential equations today. And we're going to try to answer this essential question. What are some ways you can solve an equation of the form a times b to the x power equals c, where c and a are non-zero real numbers and b is greater than 0 and not equal to 1? In other words, how do we solve exponential equations? So we kind of did a little bit of this in the prior lesson. We kind of looked back, we reflected back on when we solved exponential equations graphically in the prior module. And one way that we solved them was to first graph each side of the equation separately. As you can see here, graph each separately. And then we looked for the points where the two graphs intersected. And that gave us the solution. It gave us, in most cases, the input was the number of years or minutes or hours or whatever. And the output was the value of the function at that point, what the population had grown to or declined to, or what the money's value was, or whatever. So we're going to kind of reserve more of that graphing method now to really check our answers, and we're going to try to rely more on our algebra to solve these. So let's take a look at this little exploration. So first look at the equation 275 times e to the 0.06x power equals 1,000. So basically when I read that, I kind of think, well, that's e, so that means it's something that's growing continuously. That's like the A PERT formula, right? Or the V PERT. The value is equal P times e to the RT power. So that R is the 0.06. So that's kind of like what the rate of growth is. And so we want to know, when does a population that's growing, and I know it's growing because that 0.06 is positive. If it was declining in this situation, that would be a negative. And when does it get to 1,000? And so we could just simply take, the 275 times e to the 0.06x power and put it into y1. We could put 1,000 in y2. We could graph them, and depending on the window that we chose, it might look like something, in graphic C. And we could actually have the calculator calculate that point right there where they intersect, and we can see that that's at approximately 21.516, so about 21.5, and the output at that point would be 1,000, which is what we wanted to know, is when did the value get to. And so depending on whatever x represents, if this is money, it's probably years, 21.5 years, it's going to be worth $1,000. So now instead, if we were looking at something like this, the equation 10 to the 2x power equals 10 to the 4th. Now with something like that, we could, again, take one side, that 10 to the 2x, and graph it versus 10 to the 4th. But what you might also notice is that these are both powers of 10. That's 10 to the 2x and 10 to the 4th. And if 10 to the 2x is supposed to equal 10 to the 4th, and those bases are the same, it's kind of like, in order for that to be true, wouldn't the exponent 2x have to equal the exponent of 4? So we're trying to figure out what value would x have to have in order to make that exponent basically be 4. And that means that x would have to be 2. So that actually is a way of solving a really simple exponential equation by kind of just, thinking about this in a different way. Instead of just automatically going to the graphing calculator, see if we can kind of reason through algebraically and see if we can come up with an equation we can solve. In this case, it was simply just setting the two exponents equal to each other because the bases were the same, so we could sort of, in effect, just ignore the bases of 10. So let's go ahead and turn the page. So in addition to solving exponential equations graphically, exponential equations can be solved algebraically. One way to solve exponential equations is to rewrite them in logarithmic form. Another way is to use the property of equality for logarithmic equations, which states that for any positive numbers x, y, and b, the log base b of x is equal to the log base b of y if and only if x is equal to y. So because we have two logarithms with the same base being equal to each other, the only way that they would be equal is if those results, x and y, were the same value. Because the bases are the same, so x and y would also have to be the same in order for those to be equal. So if we kind of use that concept, and then we are able to really just sort of ignore the log base b's and just see what would make x equal to y, which is similar to what we were just doing with that power of 10. So let's take a look at this first example. 10 is equal to 5 times e to the 4x power. So let me just rewrite that again. So that's 10 is equal to 5 times e to the 4x. So just like, what's usually been the problem with these kinds of equations, the variable is in the position of the exponent. So we're going to start to kind of work our way to getting that out of that position. And so step one would be maybe to get rid of this 5. That's kind of like the coefficient here. So if I divided both sides by 5, then that would just make the left-hand side be 10 divided by 5, which is 2. And the right-hand side be e to the 4x. So remember in the last lesson where we took the log of both sides so that we could bring the exponent down? Well, that would be great if that would work in this situation if we were able to take the log of both sides and then bring that 4x down. That would take the variable out of the position of the exponent. But I have an even better idea. Because the base here is e, why not take the natural log of both sides? We'll see what happens when we take the natural log. So you could really take the log, any kind of log of both sides, but I specifically chose natural log here because now when I bring that 4x down in front, so I just simply bring this down and move it into the front, turn it into multiplication, and now that would read the 4x times the natural log of e is equal to the natural log of 2. But remember, the natural log of e is really just saying the log base e of e, which means it has to be 1. So that just sort of crosses this whole thing right out and just leaves me with the natural log of 2 is equal to 4x. And now if I want to know what x is, I can just simply divide both sides by 4. And since I have a natural log key on my calculator, I can type that in, the natural log of 2 divided by 4, and I get approximately 0.173. So that would be to the nearest thousands place. So it has to go to 3 decimal places, which I did. So what that's saying is now, if I were to take that value and I were to plug it back in, it should make the two sides equal. So I'm going to test that. 5 times e to the 4 times 0.173 power, and I get 9.98885347772, which is approximately 10. And so it checks when I plug it back in, and of course, the more decimal places I went to for my answer, the closer I would get to 10. But they asked me to go to 3 decimal places. So it's a pretty accurate estimate for what x is. Now looking at the next example, this time, if I wanted to get the part with the exponent that I'm trying to solve for, the 5 to the x power by itself, instead of dividing, I'd actually have to add because that 4 is being subtracted. So if I just simply added 4 to both sides, that would turn the equation into 5 to the x power is equal to 11. Now here would be a great place to just simply take the log of both sides. And it really does not matter what log I take here because the base here is 5, and I really don't want to use base 5 because I don't have a calculator key for that. But let's say I decided to use the base 10 log or just the common log. So I might just kind of sneak in here in front of the 11, a log on both sides. And again, why I do that is that's going to allow me then to bring that x down in front. And when I rewrite this, now my equation looks like this. It's x times the log of 5 equals the log of 11. And now I'm just simply one step away from solving, because all I have to do to get x alone is undo this multiplying of a log of 5 by dividing by a log of 5. And I can simply go to my calculator, just divide the log of 11 by the log of 5, and that gives me approximately 1.4898. So actually that's going to change this, so the 8 will round to the, will round up, that'll make 1.490. So if I were to go back and plug that back in, 5 raised to the 1.490 power and subtract 4 from it, I get 7.001839, and that is pretty darn close to 7. So that is a check. That confirms it's approximately 1.490 for x. So let's take a look at the reflect question number 2. It says, consider the equation 2 to the x minus 3 equals 85. And it says, consider using log base 2 to solve. Like I said, you can really use any base that you want. So let's say instead, okay, so it's got the base all by itself. So let's say I decided I was going to take the log base 2. So I'll just move that 85 over, and I'll take the log base 2 of both sides. So log base 2 and log base 2 on the other side. So then of course I'm going to bring the exponent down in front, and then when I rewrite that, it'll be x minus 3 times the log base 2 of 2 equals the log base 2 of 85. Well, so the log base 2 of 2, that takes care of itself because that's really just 1. And so my exact solution would come from adding 3 to both sides. It would be x is equal to the log base 2 of 85 plus 3. But then how do I figure out what the log base 2 of 85 is so that I can add 3 to it? Well, I could use the change of base property, but otherwise, I mean, 85 is not like it's some integer power of 2 or anything. So that's why, because it's going to end up causing us to have to use the change of base property. And so it probably in the first place was just as easy to use the common log of both sides instead. And this is still doable, and but you would still have to use your calculator. So in the long run, it really didn't benefit to choose anything other than the common log, or in the case of when the base is e, to use the natural log. And I think that really addresses the reflect question number 3, because that is asking, what is the benefit of taking the natural log of both sides? And that's because anytime you combine natural log and e together, that's going to just, be a value of 1. And so then multiplying by 1 is really not affecting your answer at all. So in the case of a base being e, use natural log, take the natural log of both sides, and really any other base really is not any advantage to do anything other than just the common log or base 10 log. So we're going to designate these next 2 as your turn questions, or U-turn, and so I'd like to have you guys pause the video and take a few moments to give them a try, and tune back in to check your answer. And you can also check your answer by taking it and substituting it back in the equation and seeing if the 2 sides are equivalent. So go ahead and pause the video now. Alright, so thanks for giving those a try. Pause the video if you need to check through the work if for some reason you didn't get the answers that you see here. 4.624 for number 4, and number 5, oh, it's really close. It's 0.462. just off by a decimal place. So let's go ahead and turn the page. Remember, pause the video and check your work if you need to, and see if, if you didn't get those answers, see if you can kind of figure out where you got off track. Let's go ahead and pause, or turn the page. So now, of course, the real reason why we study these things is to, again, apply to real life. So suppose that $250 is deposited into an account that pays 4.5% compounded quarterly. The equation A equals P times 1 plus R over 4 to the 4t power gives the amount A in the account after n quarters for an initial investment of P. So then again, the n is the quarters, so that's 4 times t. For an initial investment P that earns interest at a rate of R. Solve for n to find how long it will take for the account to contain at least 500. Okay, so they want us, instead of using like what we normally would use for an exponent, which would be 4 times t, they want us to call that n. So like this right here is what we normally would have as 4t, the 4 for the 4 compounding periods and t for the number of years. But they wanted us to solve for n, which means the total number of quarters. Okay, so that's actually going to make it a little bit easier when we solve, so we'll just go with that. And so when we go to plug in our $250 that we're depositing, and it's going to get paid quarterly interest, so 1 plus the rate that was advertised is 0.045, and then divided by 4, and then we're going to raise it just to the n power, and n is going to represent the number of quarters. And we want to know, when would it get to $500, or when would it double in value, in other words. So to solve something like this, we're simply going to try to isolate the part that has the exponent on it. So that's step 1. It means we're going to get rid of the 250. And dividing both sides by 250 will, of course, give me 2 over here. So it's like the problems where we were trying to find out when things doubled. And I know that 0.045 divided by 4 is 0.01127. So this is like saying 1.011, I might have said 27, it's 25 to the n power. Okay? And I know that my next step, and you can tell I left the space for it, is I know the next step is I'm going to take the log of both sides. So I'm going to go ahead and take the log, and I'm going to then bring the n down in front. And when I rewrite that, this will be n times the log of 1.01125 is equal to the log of 2. And so the last step to solve is I'm just going to simply divide both sides by the log of 1.01125, and that should give me my answer for n, the number of quarters, meaning the number of times over that all that time that was invested, the number of times it compounded. So the log of 2 divided by the log of 1.01125 is, so this is what my value of n is approximately 61.959. So that's about 62 quarters. So we'll take about 62 quarters, or which is about, if I divide that by 4, that means about 15.5 years. So about 15 and a half years for the account to get to 500. And we could check that. We could go back and put it back in. So 250 times 1 plus 0.045 divided by 4, and then raised to the 62 power, or the 15.5 times 4. So raised to the 62 power, and we get 500.229. So $500 and an extra 23 cents for your extra little bonus there. So about 62 quarters, or about 15.5 years. So to wrap this up, I'm going to have you try your turn question. That's hard to say. Anyway, and the only thing different about this one is that now we're trying to get our money to triple, but it's the same rate of return, the 4.5%. It's still compounded quarterly. So it really is just a matter of, instead of your money doubling, which was the case in this situation where it got to 500, we want the money to triple. And so really, even instead of just going back here and even putting in 750 there, we don't really need to do that. All we need to really do is change this number right here to 3. Okay, so all of these will change to 3 because now we're trying to triple our value. And so our calculation would look like this. Our calculation would be, let me just get rid of those cross outs, and it would be the log of 3 divided by the log of 1.01125. And that's going to tell us what n is, the number of quarters. So really, if we just want to know when our money triples, then that's just changing that to 3. If we wanted to know when it quadrupled, we change that to 4. But the rate of return, that 4.5%, is still kind of just kind of fixed. So go ahead, take a second and plug that in, test it out, and plug it back in and check it to see if your money actually does get to 750. And you can tune back in and we'll wrap up this lesson. Okay, so that turned out to be 98 quarters, or about 24 and a half years. So over that 24 and a half years, the interest will be paid quarterly 98 times to triple your money. And of course, if you plug back into the original equation, you can check the value, and I'm going to do that real quick right now. So if I plug it back in and raise it to the 98th power, I get $748.30, which is pretty close to 750. And you know, of course, these are not exactly perfect answers, so we're just trying to get in the ballpark, and $748 is in the ballpark. So let's go ahead and wrap this up. So it says describe how to solve an exponential equation graphically. Well, we've talked about that a lot now. So we just simply set one side up in y sub 1 and the other side of the equation in y2, and we can do that calculate intersection function in our calculator and see where the two graphs cross, the point they share in common. And then 8, describe how to solve an exponential equation algebraically. Well, in most cases, this has involved isolating the base, taking the log or natural log of both sides, bringing the exponent down, and then undoing any of the operations that need to be undone to eventually get the variable alone. So the key is getting that variable out of the exponent, and that involves taking the log of both sides. So that does it for today's lesson. Thanks for coming to class.